with vertex J, what that means is JK and JL have to be congruent to each other. So x squared plus 4x has to equal 12. Since this is an x squared, it's a quadratic, which means it has to be factored. So we need to move the 12 to the other side. So we get x squared plus 4x minus 12 equals 0. So we have to factor this. So we're looking for two numbers that multiply together to give you negative 12. And the reason why we're picking negative 12 is because a is 1. 1 times negative 12 is negative 12. They have to add together to be 4. So we're looking for two numbers that multiply together to give you negative 12, but add together to be 4. The answer is 6 and negative 2. 6 times negative 2 is negative 12. 6 plus negative 2 is positive 4. Now we're going to take this 1, that's the a value. We're going to divide both of these by 1, and the bottom number gets the x. This helps us make our factors. Our first factor is 1x, and then plus 6, 1x minus 2. So my answers are going to be x is equal to negative 6 and positive 2. Okay, so dilation is a transformation that changes size of a figure, but not the shape of the figure. The center of dilation is a fixed point in the plane about which all points are expanded or reduced. A scale factor is the relationship between the distances from the center of dilation to the image point to the pre-image point. Remember, dilations create similar figures, which means the side lengths of the two figures are proportional. If I'm looking at a reduction is a dilation that has a scale factor. Reduction means smaller, so the scale factor has to be less than 1. And enlargement means that the figure is getting bigger, which means it has a scale factor greater than 1. So I got two shapes here. My first triangle is triangle RXT. This is called my pre-image. Then my image is triangle R prime, X prime, T prime. Because that's the new image because it has the tick marks on it. This entire length, X prime to T prime, is 12. So since I'm going from small to big, this is an enlargement. To find the scale factor, since I'm going from small to big, to find scale factor, we take the big side and we divide it by the small side. The two corresponding sides, in our case, are going to be 12 divided by 4, which is 3. So the scale factor is 3, meaning the side lengths get 3 times bigger. So if I put a shape on a coordinate plane and I look at my problem and the center of dilation is at the origin, all I have to do is take the scale factor and multiply it by the x value and take the scale factor and multiply it by the y value to get my new coordinates for my new image. So in example number 2, I've got triangle PZG. The dilation rule is n equals 2. That means that the scale factor is n equals 2. This is going to be an enlargement because it's a number greater than 1. Since they didn't tell us where the center of dilation is, we assume that it's at 0, 0. So this is easy. All I have to do is come down here to the pre-image, multiply both answers by, or both coordinates by 2. Zero times 2 is 0. Negative 2 times 2 is negative 4. 2 times 2 is 4. Negative 1 times 2 is negative 2. And negative 2 times 2 is negative 4. And 1 times 2 is 2. So come over here, let's graph this. 0, negative 4 is my G prime. 4, negative 2 is my P prime. And my Z prime is negative 4, positive 2. My center of dilation again was at the origin. Can you see how these points expanded away from the center of dilation, but they're still collinear with the original pre-image points? Also, if I look at just like counting, if I wanted to go from the center of dilation to point Z, I would go up 1 to the right 2. But if I go from the center of dilation to point Z prime, I go up 2 over 4. Well, those numbers are doubled because the center of dilation and the scale factor was 2. So what happens when the center of dilation is not at the origin? We have to follow this funky formula or use our common sense. So first off with the funky formula. First thing is, since the center of dilation is not at the origin, we have to move it to the origin. So you have to go left so much and down so much. That's where this minus h minus k comes from. We have to move the center to the origin. Now, depending on which way we're moving, this may be a plus h or a plus k. It just depends on if we're moving left, right, up, and down. After we move it to the origin, we can just simply apply the rule, which is multiply by the scale factor. That's what n is. And then once we're done, we have to take our shape and we have to move it back to where it belongs. So we have to undo the moving the center. So we have to move the center back. So even though the formula looks kind of crazy, it's really easy to use. So I wanted to bring the rule with us so we have it. So it says, write the coordinate notation that describes the dilation centered at 4, 3. So we know the center of dilation has to be at 4, 3. That's right here. That's important. And it has a scale factor of half. So if I want to write the rule, we start with our normal x, y, and we're going to transform it. Just following the rule up here at the top. It says parenthesis, then it says n. Well, our n is half. Then it says parenthesis again, x. And we need to figure out what the h is going to be. Well, the h is 4. And are we moving, when we go from the center of dilation to the origin, do we move left or right? We're going to end up moving left 4. So this is going to be a minus 4 in the parentheses. And then at the end, we transform it back. So we're going to do plus 4. I would pause the video now, try to do your y's, and then come back and see if you got it right. To do the y value, it says n, which is our scale factor, times it by whatever the point is moved back to the origin, which in this case we know the k is going to be 3, and we're going to go down 3, so that's going to be a minus 3 in parentheses. Then we have to move it back when we're done, so we're going to add 3 at the end. So here's your rule in coordinate notation. this thing is going to be a reduction because scale factor is half. So if we take this rule and we apply it down here, the x value, we're going to do 1/2 times, what's the x in my coordinate notation? That's -4. I'm going to subtract 4 from that according to my rule, and then I'm going to add 4 to my answer. To get the y values, I'm going to do 1/2. My y value is now -2. I'm going to subtract 3 from that, and then add 3 to my answer when I'm done. So when I go through this process, all I did was substitute in the x and the y values for the original coordinate. Do my parentheses first. So what's -4 minus 4 is -8. Half of -8 is -4. And then we add 4 to it. We end up getting 0. Do the same thing with our y's. -2 minus 3 is -5. Half of -5 is -2.5 plus 3. -2.5 plus 3 is 1/2. Now you go through and try the other 3 that are left. Pause this video. So when you go through, these are the answers that you get. Now go plot these on your graph. And connect your dots. If I connect a line from the center of dilation all the way to M, do you notice how M prime is halfway there? And if I draw a line from the center of dilation all the way to J, hopefully you can notice that J prime is half the distance if you looked at the slopes like we did in example 1. And so on and so forth. I could do that for all of them. This is called a vanishing point. See how it moved towards the point of dilation, even though it shrunk? Even though the side lengths are half the size, it moved. Okay, how do I prove the side lengths are half the size? I would have to find the distance of every single side. So let's say I found the distance from H to N. I would get 2 square roots of 5. So the distance from H to N, the original distance, was 2 square roots of 5 when I do distance formula. And if I look at H prime, N prime, my slope, and I use the distance formula, I would get the square root of 5. Well, do you notice how H prime, N prime is half the size of HN? Okay, so that's how we know that our scale factor is right and that we followed the process correctly.